Okay, so in this particular question, what have we been asked to do? So we've been presented with an equation. Yeah, as you can see, this is the more or less the combustion of methane. But one of the things you'll notice about the question is actually the fact that CH4 is what is in excess in this question, rather than O2 being in excess, which might have been maybe what you might usually expect to be the description. The relevance of that to this is the fact that given that CH4 is in excess, the limiting reagent in this reaction is not the CH4, it's going to be the oxygen, okay? And because the oxygen is the limiting reagent, therefore we can basically infer that whatever is being produced as far as the H2O goes is going to be effectively coming from in relation to the oxygen, right? Not necessarily anything else. And although it's not mentioned in the question, one of the assumptions that's been made in this question is that the only kind of combustion which took place as far as the stoichiometry of this particular question is a complete combustion, right? So although it's not mentioned in the question, based on the context, you can kind of infer that what has taken place here is complete combustion. And the relevance of that is that, okay, well, in the context of complete combustion taking place, there would not be side products such as carbon monoxide, right? Which is obviously relevant when it comes to considering the production of the H2O, like how much is produced basically. But anyway, let's go into this. So how would we work this out? Right. Well, one of the key things to pay attention to is the molar ratios, right? So what we're effectively doing is we're using our knowledge of the mass of oxygen that was on the reactant side. We're using that knowledge to effectively be able to work out, well, what was the mass of the H2O produced effectively, right? And what we can figure out from this is that, well, and by the way, this is a balanced equation, right? What we can figure out from this is that the O2, we've got 2 O2, right? So we've got 2 O2 on this side, and we've got 2 H2O, right? What does this tell us? Well, on a molar basis, it tells us that for every 2 moles of oxygen that was on the reactant side, we're going to get 2 moles of H2O produced. So if we effectively reduce this to the lowest common multiple, we get a ratio effectively of 1:1. So effectively, for every mole of oxygen, there's going to be 1 mole of H2O produced. And so if we can work out the exact moles of oxygen that was produced, we can use that and say that is also equal to the moles of H2O. The moles of oxygen that reacted is the same as the moles of H2O produced, right? So this is what we can effectively figure out. So let's go through that process. Let's work out the number of moles of oxygen, first of all, and then we'll go from there, okay? So how do we do that? Well, we need the molar mass of oxygen, right? So we're going to need to get the MR of O2. MR of O2, right? And to get that, we'd obviously start with the MR of oxygen, right? So MR of oxygen. So if we look over here at the periodic table, you can see I've got the oxygen here, and the relative atomic mass 16 is effectively the you could say it's the molar mass of oxygen, singular oxygen. So that's 16, so that would be 16 grams per mole if we put it in the units. And to get that into the MR of O2, we'd have to, of course, do 16 times 2, right? Which is going to be equal to 32 grams per mole, right? And now that we've got the MR, what we can do is say, okay, well, using that MR, we're going to use the other figure we've got, so 32.91 grams. And if we refer to the equation, if we've got a given mass, right? So in this case, it's that 37 point, So if you've got, let's say, a certain mass, so mass M, in this case in grams, that is equal to the moles, right? In mole, right? Multiplied by the molar mass. So that would be multiplied by the MR, which, as we know, is going to be in grams per mole, right? So this is effectively the equation we're going to leverage to work out the number of moles. And if we rearrange this, if we divide both sides by MR, right? Divide both sides by MR. Obviously on this side it would cancel, and we simply get that the moles is equal to, and I'm just going to write mole, right? So mole is equal to the, actually, let's just make this a bit more precise. If I'm going to abbreviate mole, I'm going to just use N as mole. So N is equal to the mass divided by the molar mass, right? And we know that the mass in this case is 37.91, right? Grams. And we're going to divide that by the molar mass, which we worked out just now as being 32, right? So what is that going to give us? Well, that's going to give us, I would invite you at this stage to actually have a go work this out on your calculator to see what value you get, right? But if you do that, what you should find is that you get 1.1846875, okay? And that is in moles, right? So this is the number of moles of oxygen which is reacting. And because of the ratio which we just discussed and established, the 1-to-1 ratio, we know that so that's the moles of, so we can say the moles of O2 is that, and then we say therefore the moles of H2O is also equal to the same thing, right? So it's equal to 1.1846875 moles, right? Because of the 1-to-1 ratio. Now, at this stage, what we can do is figure out the mass of H2O, which is what the question asks us to do. But in order to do that, we're going to need the molar mass of H2O, right? Which we would know from the this equation tells us that, right? The mass is going to be equal to the moles multiplied by the molar mass. We have the moles now. We need to work out the molar mass. So let's work out that, right? You may already know what that is, but I'm just going to go through these steps. MR of so I'm going to write this as actually MR of H2O is equal to, right? Now find the MR. So that's going to be so we've got 1 and then 16. So it's going to be, so we know the MR as we have it above anyway, but the MR, I'm just going to write this again. The MR of oxygen equals 16. The MR, I'm just going to put the units as well. The MR of hydrogen is equal to 1, right? right? Now, therefore, the MR of H2O is equal to 1 times 2, right? So H2 plus 1. Well, if I'm just gonna swap the order I'm writing this. No, actually, I don't need to erase anything because it is 16 anyway, right? So but instead of 1, I was write 16. So 16 times 1, right? Because we've only got 1 of the oxygen, but that just makes it a bit more clear what I'm relating that to. So this is the MR of hydrogen, the MR of the oxygen, and of course, when we work that out, that's going to give us what? It's going to give us 18, right? So with this 18, we can say the MR of H2O is 18, as we've done, and we can now use that with the mole figure that we worked out to work out the actual mass of the H2O, right? So therefore, we can say the mass of H2O is equal to 18 multiplied by 1.184687.5, right? And so feel free to have a go, see what you can work out what that is, and that effectively gives us closer to the figure that we're looking for, right? So that's going to tell us it's going to be 21.324375 grams. Okay, now do we have our answer? I mean, we've got a figure for mass, right? So we're going to need to check our question. The question makes something very specific of a request. It says, please give your answer to a maximum of 2 decimal places. So given that constraint, can we reasonably say that this is our answer? No, we can't, because it's not to 2 decimal places. So we're going to effectively need to do some rounding. So we're going to say that's going to be equal to 21.32 grams, right, to 2 decimal places. Okay, so that is effectively our answer in this case, in terms of our mass of H2O, right? So